here. Let's pull out our equation. Okay. First step, let's take this anti-clockwise as positive. We have 1, 2, 3, 4. 4 terms here that we have to put here. Okay. So first one, FO cot cosine omega t. How are you going to draw this? It's very similar to this, right? So if you have FO cosine theta, instead of A, this is going to be FO, and instead of theta, it's going to be omega t. Alright, to say that? Yeah? So let's translate this one. The first one is very straightforward. So we are looking at the forcing function here. FO cosine omega t. So we know that angle is FO here and omega t. That's the angle. Right, at a particular angle. Vector at a particular angle. Okay. Next term, we have m omega squared x cosine the angle here. Alright? How are we going to represent it? So let's find the angle first. Omega t minus phi. Right? We have drawn omega t. Right here, this reference, minus phi is going this way or that way? Clockwise, right? Anti-clockwise is positive. So if I were to say this is clockwise, let's say this angle is phi. So you have plus omega t minus phi. You will get plus this angle here. So this vector is going to be m omega squared s. Let's look at the third one. Minus c omega x cosine the angle. So let's look at the angle first. Omega t minus phi plus I over 2. Okay. So where do you think? Okay, omega t minus phi brings us here. Alright? Plus I over 2. What's I over 2? 90 degrees. Right, plus is anti-clockwise, so the vector should be somewhere here. But the magnitude, be careful, is minus. So if it's minus, goes the opposite direction. Okay, so we have c omega s here. Center. Let's try the last one. For spring, we have minus kx cosine omega t minus phi. Where do you think the vector will be? So let's start from here again. Omega t minus phi is going to be here, but because it's minus, it's going to be opposite side of n omega squared. Do you want me to repeat this? Right, we have solved for, we have reached our equation as such. Right, to solve for this, you know this earlier, we used the reduction formula to change the sign to cosine so that all are consistent, so that it will be easier for us to solve using our vectors. Okay, so with each of these terms basically is going to give us a vector of the diagram. Right? We need to decide the angle of it, right, and the magnitude of it. Okay. So to start, we know we have 4 terms. It's going to have 4 vectors on the diagram. I'll just start with the easiest, FO cosine omega t. Right? So omega t, this is the angle. Anything inside the bracket of the cosine is the angle of the vector. Right? So FO cosine omega t. Earlier on we saw if we have A cosine theta, right? Our vector for our A will be angle theta. So likewise now we have cosine omega t. This will be our angle instead, and this will be our vector instead. Right? So let's draw. Let's draw this on the diagram. Taking this as the reference plane, positive anti-clockwise. Omega t is the angle. We draw omega t anti-clockwise because it's positive. And the vector O over here. Right? So that's all for our first term here. FO cosine omega t. And we have to do the same for all the other 3 terms. Right? Second term, this is going to be our vector, and this is going to be our angle. Right? So the angle first, you have to find which position of it in the diagram. So if we have omega t here, from the omega t, we minus phi, you get the position on the diagram. And because it's plus, so it's on the same side, we have m omega squared s. Is that clear before I move on? Right. It's quite common to ask you to talk about this exam. I'm sure you understand. Right? If you ask it again. Yes. Minus phi here. Oh, let's say your phi is maybe somewhere just here. No difference. Not much difference. Later when you see, when I move to the second part, when I put all of them together. Okay? So let's go to the third term. Minus c omega x cosine, whatever is this, the bracket. This is our angle. So we have done omega t minus phi from here, we know it reaches here. Now we have plus I over 2. Right? We want to add 90 degrees to this, right? So 90 degrees here. Plus is anti-clockwise, 90 degrees. We know it's somewhere over here. But because the perpendicular is minus, right, it will shoot 180 degrees the other way. So you write your vector as C omega S. And the last one, omega t minus phi, again is over here in this line. But we have minus sign. Again, it goes 180 degrees to the other side. And you add AS. Okay. So now we want to add all these vectors together. Right? All these are added together equals to 0. So we put them all in a polygon. Phi here, phi is the angle here. FO is to the angle of f omega square, which is this angle phi. Now we're going to have a closed polygon. Sorry, let's draw this side. This guy is. Right, if we have FO here. Okay, as a polygon, we draw this line, please. Okay, so this line here is my FO. This is going to be my phi. Right, my four vectors, if I add them up, it's going to be a closed loop. This is represented here in the polygon. So with this, now we can solve, we can derive many equations from it. Right? So we make our solving of our equation much easier. Okay. So let's say if you want to solve for an amplitude x, right? want to solve for x, how am I going to solve it for this polygon? You can use any geometrical relationship. So we know here is 90 degrees. Right, if you draw a triangle out of this polygon, I'll be able to apply Pythagoras theorem and get a relationship of x. Right? So this displacement here, what's this length here? So if I want to apply Pythagoras theorem over this triangle, I need to know this length, right? What's the length? Why? Why are you introducing another? So we have kx here, we have m omega squared x here. So it's basically the subtraction of this, right? Right? This length is this whole length minus this, you will get this length. Right, Pythagoras theorem, c squared equals to a squared plus b squared, where c is your hypotenuse. Now I can just put in f whole squared is equals to, what is this? What's this length here? C omega x, right? So I have c squared omega squared x squared plus b squared. Right, is that clear? Do I need to repeat? No? Okay. So very straightforward. What we do is we just look at this triangle and we apply Pythagoras theorem so that we can get a relationship of x in terms of all the other terms. Right? X is our amplitude. So now let's bring the x over one side. We will have right, so I bring my f4 divide by f4 squared. This whole term 1 equals something. And bring the square over up square below. Okay, let's do some math here. Okay, what I'm doing here is I'm just multiplying the denominator by a squared over a squared. Right, so this is a squared divided by a squared. Likewise, a squared over. did see k squared over k squared. Can I just multiply by k squared at the bottom? No, you cannot super just you want k squared over here, you put k squared, multiply by k squared. Why I can do this is k squared over k squared is 1. Right? I'm multiplying by 1, I'm not affecting the equation at all. Right? If you just put multiply by k squared below, just because you want to cancel out, the whole equation is going to be wrong. Right? So you can easily put f to the power of n over f to the power of n as well. It will not affect the equation because it's equals to 1. So I've simplified this. A over k is 1. Then I bring out the k squared. When k squared square root is k, put it up. Let's simplify further. Some that we are familiar with. Theta is frequency ratio. The possible frequency over your natural frequency. Theta is our damping ratio. CO is our critical damping coefficient. C is just our damping coefficient. So with that we can substitute our omega over omega n as theta. Okay, I will substitute for distance here. So you have theta squared, this whole term. You have m cancel, omega n can cancel with omega n squared. That will give us okay. So we have derived this attribute is 4.8, which is given in your expression. Right, no OEM too early is given, but sometimes you are asked to prove how you derive this. You can check your past. So let's look at the data sheet, what we have covered. Alright, you copy first. Okay, so if you refer to your data sheet under force vibration, right, our second part of this lecture, right, we have shown, we have derived our equation of motion, our forcing system, our right hand side now as a forcing frequency, with a steady state version of such, where S is equal to this, which is what we have just derived. And the phase angle phi is going to be this, which I will show you very shortly how we can derive this, where beta, the frequency ratio is omega over omega n. Right? So this part, let's have a look how we're going to derive for our phase angle phi. So let's go back to our polygon. Okay. So our phi is here. We need to derive for that. How are we going to do that? By geometry, what relationship can we get from phi? So again, from the triangle, if we were to use tangent phi, which is opposite over adjacent y OA, we have our opposite as c omega x, and our adjacent as this. Right? So with that, again, doing some substitution and simplification, we derive what we have on our data sheet. Okay? So I've expanded it, I'll leave it to you to sort it out yourself. So we'll show that if derived tangent phi is 2 zeta beta over 1 minus beta squared, which is as shown in your data sheet. Right, finally, let's look at how the graph will look like if we were to plot x over FO against our frequency ratio. If you were to turn to page 28 of your notes, right, so let's look at this graph here. What we are doing here is we are plotting the amplitude S over FO over frequency ratio, which is equal to beta, omega over omega n. Right? So let's look at this equation that we have derived. What happens if beta is equals to 1 and zeta is equals to 0? Okay? So beta is equals to 1, 1 minus 1 is 0, and zeta is 0, is 0, the whole denominator goes to 0. Right? This is your S. Right, anything divided by 0 is infinity. Let's look at this. So if beta is equals to 1, which is here, right, then your zeta is equals to 0, which means there's no damping, right? The damping ratio is 0. If there's no damping, it will go to infinity. Right? It's at resonance. Beta equals to 1 also means, right, if your beta is equals to 1, beta is omega over omega n equals to 1, means your positive frequency is equals to your natural frequency. What happens? Hallelujah, resonance, right? Remember, right at natural one, always, I told you before, why it's so important we need to derive for natural frequency? Because when you have a positive frequency that is the same as your system natural frequency, you get resonance. Right? That is where you get the highest amplitude. You can see when beta is equals to 1, this whole line, you get the highest amplitude. Right? Here, what we have here, they are all displaying the zeta value. So as zeta increases, but there's damping, it's going to bring down the amplitude. Right? So you can see corresponds as okay. So from this graph here, I'll just write some notes on the graph.
Zeta 是哪个 Zeta 又是上一个哦，是 Zeta
Right, so if you are beta equals to 1 and there's no damping, our S is going to be approaching infinity. So another thing we can observe is as zeta increases, right, our denominator is going to be very large. And if our denominator is going to be very large, this is going to translate to the reduction of M. Okay, so in this equation again, if our zeta is if our zeta is increasing, right, denominator becomes big, your x will become small. Okay.